Hello, everyone, and welcome to the Frontiers of Parameterized Complexity. The last lecture of this year will be given by Parinya Chalermsook, and he will speak about Vertex Sparsification for edge connectivity. And I hope I didn't mispronounce your name too badly.
No, it's good. Yeah.
Okay, please. The floor is yours, please.
Yes. Yeah. Okay. So, right. So before I start, I can, if you want to ask questions, if I say something unclear, just feel free to ask me anytime. You can type in the chat, but if I don't see, you can also turn the mic and start the shouting. I don't mind. So I don't mind to be stopped anytime. So just shout. And okay, so then I will just start. So this talk is about in a broad theme, this is about graph compression or graph simplification questions, but we will look at parameterized version of it. So what is it about this graph simplification questions? So in a broad view, you are given some graph G and some important information that we want to maintain. And the goal is to construct a much smaller graph that contains exactly the same information or kind of approximate information. Depending on the situation, this meaning of approximate and the size of the graph we want could be different. For example, so this question actually appears a lot in the literature of graph algorithms and approximation algorithms and parameterized algorithms. For example, we may want to preserve like this important information could be information about cuts in the graph or the distances between some terminals in the graph. And the notion of simple graph that we want to maintain can be, for example, I want small number of vertices or small number of edges, or maybe I want the structures to be easy, like trees or planar. So this question appears a lot, like this family of questions. And so in this talk, I will focus about the graph simplification that preserve cuts. And so let me define this formally. So I'm given a graph and a subset of vertices that I call terminals. And I define the notion of cut. So I define this function cut between A and B. So A and B is the partition of the terminals into two sets. So cut AB equals to the value of minimum cuts that separate A and B. Yeah. So, and the goal is to construct what we call mimicking network H of G. So I just say G, but actually I mean G and T. Yeah. So mimicking network H of G wants to guarantee that for every such partition of terminals, the value of cut that separate A and B in H is the same as the value of cut, the minimum cut that separate A and B in G. So we want to preserve, so in some sense, we want to preserve all the minimum cut values between the terminals. So one should think of these terminals as being much smaller than the size of the graph. Maybe I have like 100,000 nodes in the graph, but I have only 10 terminals. And the question is, how large do I need H to be? And large means the number of edges, the number of vertices, or whatever. In this case, we care about the number of edges and vertices. So there is another name that appears in the literature. So this is also called Sparsifier. And it has also, the approximate version of it has also been studied. Like instead of preserving the cuts between terminals exactly, we just want to preserve the cuts like approximately, let's say within a factor of 2. So, but in this talk, I will focus on the exact version. So let me give some example. This could be my G and my terminals. I have 3 terminals A and B and C. So this is the input graph together with the input terminals. I have three terminals. I want to claim that I don't need to, if I only care about the cut size between the terminals, I don't need to keep all these vertices. I only have to keep one vertex in the middle. It will preserve all the minimum cut size between A, B, and C. Like if you look at, this is just because if I want to separate A out of the other terminals, I need just to cut one edge. And this is the same for H. So this, you can see that I don't need a lot of vertices in the graph. So the question is, in general, how large the graph H needs to be. So is the problem clear? Okay, so if I don't hear anything, I will just keep going. So this object is called mimicking network or sparsifiers, and it has found a lot of applications. For example, Moitra used it as a general tool for reducing approximation factors. If you have some cut problems and your approximation factor is like log n, depending on the size of the graph, if the cuts that you care only depends on k, the size of terminals, then instead of running the cut algorithm on the original graph, you can run it on this sparsifier, and the log n approximation turns into log k. Yeah, this is an example. And so in this talk, we will show that. So I will show you that there are actually like two more applications that you can get from this object, even the parameterized version of this object. So, okay, so I will show you that it can be used to compress the dynamic program table, and also for like answering like fast dynamic queries. Okay, so in general, the mimicking network or the sparsifier that I just defined, the problem with it is that it's too general because you want to preserve all the cuts, and therefore it faces information theoretic limit. There is an upper bound of 2 to the 2 to the k, so k is the size of the terminals. So it is shown that the mimicking network of size to like double exponential exists, but also there is a lower bound of 2 to the k. So basically, this bound is pretty bad in terms of k, and it doesn't give the applications that we want. So, right. So basically, one cannot, although this object is very useful, one cannot expect to get good bounds out of it. So that's why we ask a parameterized version of it, and it will allow us to actually get good bounds, and then the construction can also be done efficiently. Okay, so the object that I just defined, it can be used to solve cut problems and connectivity problems. But what if I just want to use it for the purpose of connectivity problems? Not even that, just low connectivity problems. So let's see what I mean. So I want to define, like now C is another parameter. Connectivity C mimicking network is a graph H that preserve the cuts between terminals, but not all the cuts. I just want to preserve the cuts up to the value of C. So if my cut is larger than C, I don't care. I just say that I will just keep C. So anything that is bigger, I just want to, as long as I round it down to C, it will be okay. So yeah, so let me try to define this formally. So what I show on the left here is the definition of mimicking network. And now I want to define connectivity C mimicking network. So first, I define the notion of thresholded cuts. So for any partition AB of terminals, the thresholded cut, so the cut superscript C is defined as like the minimum between the cut value and C. So this is this just means that for any cut that is bigger than C, I don't care what it is. If it's 2 to the C, I also round it down to C. Okay, so this is this cut function, the threshold cut function. And now the new goal for connectivity C mimicking network here is just that for any partitions of terminals, I want to make sure that the cut size is preserved up to the value of C. Yeah. So this is the goal. So any question up to this point? So yeah, so I hope it's clear what I want to do. Okay, so now our main result. So we can first we show the existence of mimicking network of size k times c to the 4. Notice that this can be contrasted with 2 to the k lower bounds if you want to preserve all the cuts in general. If you want to preserve only cuts up to value of c, now you can get it down to linear in terms of k for constant c. And such mimicking network can be obtained only by contraction. So I will define this more formally later. And the nice thing about contraction mimicking network is that once you show the existence of such a graph, it implies immediately that you can compute it in near linear time. So basically, this should be m, not n, yeah, but it's linear times when c is constant, it's near linear. So it's m times polylog. So the existence immediately implies fast algorithm to compute it. And we show it. We show 2 applications of this object. So first, we show that we can use it to compute to solve the problem that we call C connectivity edge connected. C edge connected spanning subgraph. C edge connected subgraph. So you are given a graph with some terminals. You want to find the smallest subgraph such that these terminals are C connected. So this problem generalized Steiner tree, and our mimicking network implies that you can solve this problem in time treewidth to the treewidth times policy. So this is like a parameterized algorithm in terms of treewidth. Okay, so if C is constant, then this is treewidth to the treewidth. And so there is a lower bound of 3 to the treewidth, even for C equals to 1. So there is still gap between the upper and lower bound. And we can also use our object and the algorithm to solve what we call the offline dynamic C-edge connectivity problem. So in general, we want to do online, but this offline one, so I'm not going to define the problem because I'm not like, it's just that you are given the queries, insert, delete, and you want to ask, so the graph is dynamically changing. And at any point, you may want to ask whether the 2 nodes are C connected. Yeah, so that's the goal. And we consider the offline version of it where these queries are made available in advance. And the algorithm can see all of them in advance. And we show that there is the data structure that answers this query in polylogarithmic, like near constant update time, yeah, polylogarithmic update time. So query times. And so there is a follow-up work recently by Jin and Sun. So they showed that inspired by our mimicking network, they can actually solve the fully dynamic equation. So okay, so there are some further related works. For example, so as I said, this question has been studied a lot. For example, if you want to the sparsifier so that the size is fixed to be k, so you allow only the terminals, but not any other extra nodes, then in this case, we know that we need to lose some approximation factors to preserve the cuts. And the base upper bound is log k over log k approximation. And the base lower bound node is square root log k. So this is like when you don't allow any extra nodes. And so there are other words, like for example, there is a trade-off between what you can do between the trade-off between quality and the size of such mimicking network. Like for example, if you want to preserve the cuts up to constant size, then there exists mimicking network of size kc cube. And for spatial graph classes, method bounds are known. So I'm not going to go into the detail of this. Okay, so this completes the introduction, and now I want to show you how to construct such a graph. Okay, so if there is any question at this point, then you can ask. So I don't see any question. So I will continue. So how does one show that such a graph exists? So first I will define some preliminary terms. So if in case, just to as a reminder, so the contraction of an edge is just like if I want to contract edge UV, then it will become a node, and you just glue them like this. And whatever is adjacent to U and V, they will be adjacent to this glue node. And when I say that I contract a cluster or a subset of nodes, it just means that I contract every edge in that within that induced subgraph. So okay, so this is what I mean by contraction of an edge and a cluster. And notice that one nice thing about contraction is that when you contract, we know that the minimum cut does not decrease between any terminals, because now you are considering smaller number of cuts, so it can only increase or stay the same. And I say that, so the goal is that I want to contract some clusters so that the cuts do not increase, and then I will be done. So I say that an edge is safe for contraction if the contraction does not increase the value of the cuts that I want to consider. Okay, so and then, so in a graph, so this is the view that I will be considering our graph. So if I'm given a graph G and the terminals A, B, C, I want to view this input graph as like what we call a pull-out terminals. So for each terminal, I'm going to add edges from A to outside, and I will see the terminals A, B, C as just the normal nodes, and then the terminals will only be like be put outside of this graph G. So like there is like a set of vertices in G, and all the terminals are outside, and they have degree 1. So this will be how I view the graph. And it's easy to show that one can view it this way. Okay, so I'm not going to prove this, but yeah, you can assume that there are K times C terminals. All terminals are degree 1 vertices, and they are pulled out. Like the whole thing is a cluster, and the terminals are outside. And the mimicking network that I'm looking for looks like this. I have some pull-out terminals and the graph. I want to partition the graph into small number of clusters. And once I do this partition, I want to make sure that these clusters that I have, they are safe. Then I will contract them. So notice that in a new contracted graph, if the number of clusters are small, then this contracted graph is small. So if I can make sure that I only contract the safe clusters, like the cluster I contract do not change the value of the minimum cuts between the terminals, then I will be done. So that's the high level plan. I will partition the graph into clusters, small number of them. I will contract them, and then I'm done. I want to make sure that each cluster is safe. Okay. So what is the notion of safe? Yeah, so now I will define it formally, like what kind of cluster is safe to contract. This can be captured by the notion of Welllinkedness. So if I have a vertex set U, and then I have also the set of edges that hang out from U, the pull out nodes from U. Let's say I denote by S the boundary of U, like the boundary edges. And for each subset A of U, SA is the boundary edges that are attached to A. So these are my terminologies. I say that this class, so now I'm going to define what it means for this U to be well linked. So I say that a cut AB of U is violating if the edges that cross from A to U minus A is less than the terminals that are attached to it. So threshold by C. So if you should forget this C, and I say that the cut is violating if the cut size is smaller than the smaller size of the terminals that hang out. So this may sound, if this is the first time you see this definition, it may sound a bit counterintuitive, but my hope is that I will try to make it clear later what it means. Okay, so this is what it means to be a violating cut. Notice that any violating cut has size at most C minus 1, because any cut of size C will not be violating. So, and I say that the cluster U is well linked if there is no violating cut. So no matter how you cut the graph, there are more edges that hang outside than the edges that cross inside. So that's roughly what it means to be well linked. Okay, so I mean threshold, like apart from the fact that this is thresholded by C. So my claim is that any well-linked cluster can be contracted without changing the cut values between terminals. So if I have any cluster U, then this cluster can be contracted and the cut values remain the same between the pull out terminals. Okay, so yeah, so this is like, so basically now if I want to construct such a mimicking network, I just need to locate these well-linked terminals, like well-linked clusters, then I will be done. So like small number of them and contract. So, okay, so how do we prove this, that such a well-linked cluster is safe to contract? So I just need to show that, so after I contract, definitely the cuts cannot decrease between terminals. I just need to show that the cuts also cannot increase. Now, I want to show that between any boundary nodes, the cuts after I contract do not decrease. So let's say the cut value is Q after I contract. So let's say in this picture, Q is 3. Like, so this means that there are 3 disjoint paths from the red terminals to the blue terminals. So I show them in these paths, in these 3 paths. Yeah. So these 3 paths connect the mean cut between them being 3. It means this, that there are 3 disjoint paths in the contracted graph. But in the but what about in the graph before I contract? Do I have these 3 paths? And I want to claim that I also have these 3 paths. So, and the only thing I need to do is just that I need to somehow connect these 2 paths that go into U with the 2 blue paths that also go into U. And such paths exist because of the Welllinkedness. So the Welllinkedness say that between any subset of terminals, I will have a routing inside. So that's the idea. Like the cut will be at least 2, and therefore there is such a path. So this means that whenever such disjoint paths exist in the contracted graph, it exists in the graph before contraction. So such clusters can be contracted. Okay, so in some sense, Welllinkedness just means that it behaves a well-linked cluster. It just behaves like a router. So whenever you want to connect some incoming paths, like in this picture, there are 2 incoming paths. Whenever you want to connect up to C of them from some incoming paths to the outgoing, Welllinkedness condition always guarantees that such a path exists. So yeah, that's the idea. That's why Welllinkedness is good for us. Okay, and so this is already almost all the tools that we will use. Another tool that we use is a corollary of a very nice result by Krause and Wallstrom. One can derive this corollary rather easily, that whenever you have a graph and the number of terminals is small compared to C, yeah, then there exists a mimicking network of size C to C cube. So I'm not going to prove this, but this is like a very simple corollary of their work. So basically, if the number of terminals is small compared to C, we are done. That's the corollary of their work. But in general, the number of terminals can be much larger than C. Okay. So first I will prove the existential result, and I will show how to construct them efficiently. So is there any question at this point? I hope it's clear. Okay, I don't see any chat. Okay, so I will just continue. Okay, so here is how our algorithm works. So initially we start with one cluster that contains all the vertices between. So it contains all the vertices in G, and recall that the terminals are pulled out, like they are the edges, the degree 1 guys that are placed outside of this cluster. And the algorithm works as follows. So first, I have one cluster that is called unmarked. I haven't marked them yet. And whenever I have an unmarked cluster, I look at the size of the boundaries. They are the edges that go outside of the clusters. If the boundaries are small, smaller than 2C, then I will mark this cluster as small. Otherwise, if it's large, if it's like bigger than 2C, then I will check if this cluster is well linked. If it is, then I will mark it as large. Otherwise, if it's neither small nor well linked, then I will just find a violating cut of X into Y and Z. And then I will remove X as a cluster and replace it by Y and Z. Okay, so basically I have first I have the whole graph. I check if this graph is well linked. If it's not, then I cut into 2 pieces, and then I check each of them. If it's not well linked, I also keep cutting until either the boundary is small or it's well linked. So this process will terminate for sure because I cannot continue forever. Like, yeah, I will have at most n clusters, and a single vertex is always well linked. So it will terminate. So this algorithm, I hope is clear. So the only thing that is unclear how to compute is how to turn into efficient algorithm is the process of finding violating cut. This is what I want to note. So yeah, so this picture, I just want to show the process of kind of recursion, not recursion, like to cut one cluster into two. Here I have one cluster, and notice that this is a violating cut because there are two edges that cross, and there are three edges that hang out of each side. In this case, I will cut this cluster into A and B, and I will work with A and B afterwards. So, okay. So the goal is to show that, so for sure this will terminate. And the goal is to show that when it terminates, the number of clusters is actually small. It's only k times c clusters. Yeah, so this is what I will show. And for each small cluster, we are going to use the Clausen-Wallstorm result to replace it with like a small number of edges, like the mimicking network of a smaller size. And for each large cluster, you can just contract it because it's safe. You can contract it to be one vertex. Therefore, if this lemma is true, we are done. We will have k times c to the 4 edges in total. Okay, so now I'm going to prove the lemma. And I want to illustrate the process of this algorithm as a, like, the execution log of this algorithm can be represented as a tree structure. So in the beginning, I have one cluster. And if there is a violating cut, I will cut it into two clusters. And both of them are unmarked. And I look at the cluster on the right. If there is a violating cut, I will cut it further into two more clusters. And one of them is small. So at this point, I have three clusters in total. One is marked as small. The other two are unmarked. And then that cluster is again has a violating cut, is not well linked. Then I cut it into two clusters. One, let's say one is large, and the other is neither small or large. Then I can continue like this until the process terminates. In the end, the number of clusters I have is just the number of leaves in this tree, in this execution tree. Okay, so I just need to bound this number of leaves. And I will instead bound the number of internal nodes. So, okay, so I want to say that I do not make such cuts more often. And the way I show is we are going to use some potential function. And our potential function is just like the number of boundary edges minus 2c times the number of clusters. Okay. In the beginning, I have one cluster. And the boundary edges is k times c. So it's like just the number of pull-out terminals. So in the beginning, this potential function is k times c minus 2c. And then the number of clusters keep increasing. It's quite a simple observation that this potential function actually only decreases whenever a new cluster is created. Whenever I make one cut, okay, so yes, so let's see why. So let's look at this cluster that gets cut into A and B. Notice that whenever I cut, the violating cut always has size at most c-1. Therefore, if you look at clusters A and B, the total number of boundary edges that go out of A and B it increased by c minus 1 each at most. So here is denoted by the edges that go in the cut. So so the cluster B will have 2 more boundary edges that go out of B, and A also will have 2 more compared to before I cut. So in this case, I have 4 more, and in general, it's 2 times C minus 1 more. But notice that the number of clusters increased by 1. So the potential function will be minus 2C, but it's like plus 2C minus 2. So the potential function always decrease by at least 2. Okay, so yeah, so this means that my potential function, it starts with k times c, and it only decreases whenever I cut. Whenever the algorithm make a violating cut, this potential function decrease. And with some minor modification of potential function, one can guarantee that. So this is not going to work directly, but with a minor modification, one can guarantee that it's always positive. Therefore, this means that you are not going to make more than k times c cuts, and we are done. That it means that the number of internal nodes is at most k times c. Okay. So yeah, so this concludes the proof that when this process terminates, I will get k times c clusters, and recall that the small cluster will be, so each small cluster we will use Krashen-Rollstorm result as a black box, and for each large cluster we are just going to contract it because it's well linked. Okay. Right. So so this is the end of the non-constructive proof. So to turn this into an algorithm, notice that the only process that is not algorithmic is this one. How do I find a violating cut? So if I have k terminals, I want to be able to find a violating cut inside this. So I have a cluster. I want to, and some boundary edges that go out. I ask myself, is there a violating cut in this cluster? So this can be viewed as parameterized sparse cut problems. So you have a graph, and the terminals are pulled outside, and then you have k terminals, and we want to check if the sparse cut here, if the sparsity here is less than 1. So like with respect to this terminals. So it turns out that this problem is not quite simple. So we managed to find the algorithm that run in time like exponential of k squared. This will imply that we get a mimicking network in FPT time if we want to solve this, but then it has some bad polynomial dependency in the size of the graph. So this will not give a near linear time algorithm. Okay, so
Parinya,
okay.
Isn't this exponential c square?
Right. It's c. Yes. It's not k. Yeah. It's c squared. Yeah. You're right. So, right. Now I get confused between c and k. Yes. You're right. Right. So thanks. So yes. So the idea for fast algorithm is that now we want to, so since if we want to find a violating cut, it seems that we need to solve a very non-trivial problem. So what if we don't solve that problem explicitly, but we know from the existential result that in this graph, all the edges except for small number of them, they can be contracted. So we just need to be able to detect the edges that we can contract. So that sounds actually easier, but if you do it directly, it's also not so easy. Like to check that whether contracting each edge actually increase the value of the cut. So this is not easy to do it in near linear time. So, but yeah, so there is some trick, and it's based on the observation that this question is actually very easy. Like it's not difficult if you want to solve it in expander. So if your input graph is an expander, then actually this question of like which edge can be contracted can be solved very efficiently, like near linear time. Okay, so how does it work? Basically, there is a recent trick that was used by Foster et al. If we have a graph G that whose expansion is at least 1 over polylog, then you can actually enumerate the cuts in this graph like very quickly. Like you can enumerate all the cuts of size at most C in time in this time that, so you just see this as like m times polylog. And so I'm not going into the detail of how this is done, but the only message that you need is just that if the graph is expander, we are done. If it's like 1 over polylog expansion, if it has 1 over polylog expansion, then we are done. Okay. But the input graph may not have such expansion. So what do we do? So there is again a very useful tool due to Saranurak and Wang. They give a near linear time algorithm that partitions any graph G into expander clusters such that the number of edges that go across the clusters are small. So I will not be explicit about how small it is, but you can think of this as like, so on the left-hand side, this is not a COVID virus. It looks like one, but it's a graph, and there are some pull-out terminals, black terminals, and this algorithm allows us to this algorithm run in near linear time, and it allows us to cut this into clusters, and the red edges that go across the clusters, they are small. So now what do we do? So we run this expander decomposition, and we look at each cluster, expander cluster, and we also view the original terminal together with the edges that go across the cluster, the red ones, as terminal in this expander cluster. And we run our algorithm there because we know that we can solve our problem inside an expander. So each expander cluster can be solved quickly, and we get a mimicking network that has the same cut structure as this cluster. And the size is, let's say, if I look at instance I, then I can get the expander, I can contract them so that finally the size go down to ki times c to the 4. And now if you combine this thing, notice that now in the calculation, the number of red edges will show up. That's why we need them to be small. And this will give us that we will get the mimicking network of size kc to the 4 plus m half. So the number of edges will be half plus kc to the 4. This is still bad because it has m, but we can actually repeat this process. So if we repeat this process r times, so each time we use expander decomposition and solve our problem on expanders, and we get a smaller graph in the end. If we do it r times, it will be kc to the 4 plus m over 2 to the r. So with log m times, we are done. And each time each round is going to take only near linear time. Okay, so this is the end of the algorithm. So notice that this algorithm, it does not use the non-constructive proof at all. It only uses the fact that our mimicking network is a contraction mimicking network. So in the literature, it has like most of the known, I think all known mimicking network are actually contraction-based mimicking network. But yeah, so this proof actually shows that such a mimicking network is very friendly for fast computation. Okay, so now I will conclude. So what we show is that there exists a mimicking network that preserves cuts up to value of c, and such mimicking network has size k times c to the 4. For our applications, it's very, very important that k here has linear dependency. That's why we cannot use all known results at all. So this is very important that dependency on k is linear. And I think the obvious lower bound is k times c, but we don't know. So there is still some gap between k times c to the 4 and k times c. And we also show that there is a near linear time algorithm to compute any optimal contraction mimicking network. So whenever someone shows later that there exists a better contraction mimicking network with any kind of non-constructive proof, then our algorithm will give the mimicking network of that size in near linear time. So we show two applications, the parameterized algorithm by like the network design parameterized by treewidth. This one does not need efficient computation. Only the existential proof is enough. And the offline dynamic connectivity, which was recently extended to online. And yeah, so I will conclude with open problems. So there are several angles that come up in this work. So one can view this work from the perspective of just pure graph theory. Like we want to ask the question of like, if we want to preserve this kind of information about graphs, how large does the graph need to be? And so the first question is like, can we show smaller mimicking network, like our kind of C mimicking network? And a long-standing problem in this area is to look at the classical mimicking network that does not have parameter C. And it is not known whether there exists a, like let's say 1 plus epsilon mimicking network or sparsifier of polynomial size. This is a long-standing question in the area. And from the view of parameterized algorithm, there is also this question of computing violating cuts that comes up, and it seems interesting on its own because it's a natural parameterized variant of sparse cut. And then there is also the gap between upper and lower bound for the network design problem in the treewidth parameters. So for c equals to 1, we know that the answer is actually just a single exponential. It's not treewidth to the treewidth, but it's like 2 to the O treewidth. So what about more general c? Then what will be the answer here? I think this is an interesting question. And so, and in terms of fast algorithm, the question of dynamically maintaining our mimicking network directly is still open. So the recent work does not maintain our mimicking network. It uses a little bit modified structure. And also, is there a polynomial time algorithm for our mimicking network? I think this thing was solved recently, but like the paper was posted on arXiv by one of the co-authors of this paper. And Yes, that's it. So thank you for listening.
Yeah, thank you very much. So we have time for questions.
I have a question. First of all, thank you for a nice talk. You mentioned during the talk that when you find a small cluster, you want to apply the Crouch and Wallstrom construction to get a mimicking network. Now, one of the things that in kernelization we often bump into is that that is a randomized construction, because to get a representation of the gamoid, the best known is to use randomization. And I was wondering whether this doesn't also go through in your algorithm. So I
think we just need the existential result, because in the end we are not going to find such clusters. As I mentioned, we just want to find the edges to contract. So existential results are enough for us. Yeah.
Okay, thank you.
Yes.
Yeah. Thanks, Bart. Any other questions? Okay, seems that that's it, right? And then thank you once again, Parinya, for the nice talk. And thanks for everyone for attending. And we'll see you in the next, hopefully more happy New Year. Right?
Okay. Yeah.
Goodbye.
Thanks.
And thank you.
Okay, bye.
Bye. Thank you.